do give judgments on all that. Noah and I will confer and kind of average our grades together for your hammer blow. So everybody, hopefully nobody has a really bad back, so they can actually do it. I'm serious about it. All right. Anyways, this is kind of what you're going to see in the field. These things right here are the seismic detectors. They're essentially the geophones, the microphones that detect the sound waves from the hammer blow. Here is what's called a spread cable, which connects the geophones to a recording system. And this is a diagram, very simple diagram of how the whole thing works. So, I've got a seismic cable with my geophone. It's called an array. Okay, when I think of an array, what am I thinking about? I'm thinking about a matrix. If we were thinking about a 24 element by one column, 24 by one, that mathematically we call that a vector. But we call it an array because we can put it out in 2 dimensions. Right? So there's our geophone array. So each one of those sensors is going to detect, what's it going to detect? So let's say that I have this geophone array here, all the way to this. All right. What am I going to get in terms of a record from a hammer blow? Well, essentially what happens is when the energy source, the hammer, hits the base plate, there's a timing start signal that's sent to the recording truck or the recording unit. It says, okay, start listening now. Turn off and on, okay? And the recording truck will listen to whatever each of these sensors picks up. It'll basically be like, each one of those is like a sound file that you might get in Google or in your texting, right? You can talk. So each of these individual geophones is a sound file. So it would look, this geophone sound file might look like this. And this individual geophone might look like this. Right? Where this is time and this is X. So right away, you can see that this thing is what? This file, this record of data from the start to the end time is an array, right? It's got value of X, right, for the different sensors, and it's got time on the vertical axis. So this whole thing here is a function of X and T. It's a 2-dimensional function. And it's digital, right? There's a sample that occurs in time, just like an MP3 file. So you sample in time. Maybe you sample the data at every millisecond. So if you record 1 second of data, you have 1,000 samples in time. You have 24 different geophones. Right? So this array would have a size, possibly, of 24 by 1,000. 24,000 binary values. How many values would you have in a gravity survey with a gravimeter located at the same point? So if I change that to be a gravimeter, how many values do I get in gravity? 1. Exactly. So if I'm looking at gravity, it's just a function of X. Right? There's no time dependence to gravity. It's just a measurement that occurs at that place. So this is going to be 4 values of x. It's not an array, multi-dimensional array, it's simply a vector. So gravity is a lot easier to deal with in a computer, okay? Which is why people used it a lot more a long time ago, because they didn't really need a lot of compute power to deal with it. But imagine these kinds of data blocks. Now imagine that rather than 24 channels, let's say you had 240,000 channels for one camera block. Now imagine 240,000 camera blocks. Right? Here's the size of the data matrix. It'd be 240,000, 240,000, and 1,000. These are the number of geophones. This is the number of shots. And we're always going to call the hammer blows, we're going to use the word shot all the time. Take that down. When I think of a shot, I'm thinking of a dynamite explosion, or a hammer blow, or an air gun explosion, or maybe a fiber size, or maybe it's a microsecond, maybe it's an earthquake. So that's a big data volume, right? 240,000 plus 240,000 by 1,000. How big is that? I've got 2.4 times 10 to the 4, 2.4 times 10 to the 11, right? More than 10 to the 12. It's a lot of data. Okay. And that is why seismology works so well. Basically a big data problem. And this data volume will go through, Brett will talk about this, sometimes hundreds of steps in order to go from the collected data to an actual representation of the Earth. And people spend their lives on very small subsets of that process when they go to look for a big airplane. Okay. And eventually, hopefully, they learn the whole process. But it's a very, very complex process. So that's basically how everything works. Now, what I'd like to do very briefly here before, I'm going to try something different. Okay. So here's our recording instrument right here. All right. Now I'd like you guys to pair off in groups of 2. And I've got a couple of questions for you on this picture. So I've got an impact right here, right? And let's say that impact generates just a pulse at time 0. So this is time along this axis, and this is t equals 0. So it generates a pulse, and just like when you drop a rock into the water, right, that's a pulse as the rock hits the water, and it sends out waves. So in 2 dimensions, this thing is called a wave front. Now, let's pull this up. I'll put this back down in a second. I want to ask a few questions about that diagram. See if you can read the answers. So the first thing I'm going to talk about is the amplitude. Let's say that the amplitude of this wave is A naught. That's the amplitude of that initial pulse, how hard you hit the hammer. So first question is, what is the amplitude at a distance r from, actually I'm going to say not even amplitude. I'm just going to say, what is the energy? So let's just call this energy E naught. What's the energy at a distance r from the impact? And you have to think of this in two different ways. 2D and 3D. In other words, when r is a function of 2 dimensions and when r is a function of 3 dimensions. And the other thing I'd like you to answer is, what is the time